Quite often in Spec Evo, authors try to make increasingly alien worlds as they go further and further into the future. And intuitively, this seems all well and good, because if you were to say go 50 million years in the future, life would be as different from now as life 50 million years ago is from the present day. However, sometimes Spec Evo worlds become more and more outlandish as you go further into the future at an accelerating rate. Perhaps the best example of this can be seen in the New World segment of The Future is Wild, set 200 million years in the future. This time was dominated by invertebrates, with all the tetrapods, terrestrial vertebrates, having gone extinct. The New World had crustaceans act like fish, snails act like rabbits, and squids acting like primates. But how realistic is this? Well, we can first look at how back we need to go in time to find a world dominated by invertebrates. It's hard to pinpoint an exact date, but I'd say the youngest point would be the start of the Devonian 419 million years ago, while the oldest point is 444 million years ago at the start of the Silurian. In the Ordovician, pretty much all of the niches in the ocean were filled by invertebrates, with only a few jawless fish swimming around. Meanwhile, in the subsequent Silurian period, jawless fish diversified, filling many of the free-swimming or nectonic niches. Meanwhile, various arthropods such as trilobites dominated the seafloor, and the Eurypterids filled the apex predator role. In the latter Devonian period, jawed fish diversified, most notably the armored placoderms, and many, such as the iconic Dunkleosteus, filled the apex predator niche. So, at this point, you could say the age of the vertebrates had begun. However, you could also say that invertebrates are still dominant, because insects make up the majority of animal species alive today. Furthermore, it's estimated that the total biomass of insects comprises about 1 gigaton, which is more than all of the mammals, including humans and livestock, which collectively make up 96% of all terrestrial mammalian biomass. But when dominant is discussed in ecology, it usually refers to large herbivores and apex predators. It is a bit of an arbitrary and anthropocentric definition, but these are the roles Spec Evo focuses on, so it works for the sake of this video. So, is the idea that invertebrates could end up filling most of the niches vertebrates fill now plausible, and how much can we really expect the global ecology to change as we venture a set distance into the future? To get an idea of this, let's look at a chart of the extinction rate over time. While we do get some spikes or mass extinctions, there is also a background extinction rate. This can be seen as a regular faunal turnover rate, but instead of being constant, we can see that it's declining over time. As such, the fauna of today will probably be more like the fauna of 50 million years in the future than that of 50 million years in the past. How different? Well, to get an idea, we can put this curve on the graph that roughly corresponds to the background extinction rate. Taking the approximate values at 50 million year intervals, we can get an equation for the background extinction rate as a function of time. This is 1.315 multiplied by e to the negative 0.00471 multiplied by the time, or t. How much the fauna has changed between two time points would be the shaded area under the curve, or the integral of the equation. The antiderivative of the equation is negative 279 multiplied by e to the negative 0.00471 multiplied by t. The difference between 2 points doesn't give much of a meaningful value on its own, but we can use it as a relative term, i.e., we can see how the difference between two time intervals compare to each other. For example, we can see that the difference between now and 50 million years in the past would be 27% larger than the difference between now and 50 million years in the future. Basically, the faunal composition of the Earth is changing at a decelerating rate as we go further into the future. Keep in mind that this trend has persisted throughout the Phanerozoic, or as long as animals have been a thing, so it's unlikely to be reversed anytime soon. We can go further and figure out how far in the past we'd have to go to see a world as alien as a world set at a given time in the future. To start, we can say the difference between now and a point in the future, d, is equal to negative 279 multiplied by e to the time in the future multiplied by negative 0.00471 minus 279. To calculate how far in the past we'd have to go to get the same difference, we set d equal to negative 279 minus negative 279 multiplied by e to the time in the past multiplied by 0.4471. Solve for the time in the past, and we get this equation. When we plot the time into the future and the past equivalent, we get this trend line. The fauna of 100 million years in the future would be as different from the fauna of today as the fauna of today is from the fauna of 68 million years in the past. The fauna of 200 million years in the future would be as different as the fauna of 101 million years in the past, and the fauna of 300 million years in the future would be as different as the fauna of 119 million years in the past was. This deceleration will continue as it approaches the equivalent of 147 million years in the past. This asymptote is an artifact of the model we used for the equation. This was an exponential decay function, and this is a finite integral, meaning that as you start from a given point and go to infinity, a finite area will be under the curve. In this case, the integral from the present to infinity is the same as the integral from 147 million years in the past to the present. This makes the notion of a world dominated by invertebrates, or one as different as 444 plus million years ago in the past was to the present, pretty unlikely. Of course, real life often has many confounding variables and is usually too messy to fit into a single equation. For example, the short-term oscillations in the extinction rate are larger relative to the overall background extinction rate as you get closer to the present, suggesting it may be moving away from an exponential decay pattern and moving toward a sine wave as time moves forward. A sine wave will have an infinite integral, meaning the fauna will become increasingly alien in the future over long time frames at a relatively constant rate. If we assume this transition starts now, we set d equal to the current background extinction rate, 1.315%, solve for the past integral, and get this equation. When we plot it over the next billion years, we can see the future will seem more alien, with the fauna being as different from that of today as the fauna of today was from the fauna of 360 million years ago. Stretch this trend out a few more billion years, we can see that by about 1.5 billion years in the future, we do get a world as alien as that of 444 million years in the past, i.e., the invertebrate world. But, while the aforementioned trend has persisted for a very long time, how long can it persist into the future? Well, for one, it can't go to infinity, as the Earth will eventually be swallowed by the Sun, and before then, the Earth will be sterilized. Exactly how this will happen is a topic for another video, but we can take forecasted future events to set boundaries for this trend. One limit could be 600 million years in the future, where continental weathering will cause carbon dioxide concentrations to dip below the level that C3 plants need to sustain growth. This might cause serious perturbations to the global fauna, but it wouldn't be the case if the shift from C3 to C4 plants was gradual. But another limit would likely be at 1 billion years in the future. At this point, the solar luminosity will have increased sufficiently to cause the evaporation of the oceans, leading to a runaway moist greenhouse. This would cause the global temperatures to exceed 50 degrees Celsius. While some hardy hyperthermophilic prokaryotes can grow in temperatures in excess of 100 degrees Celsius, the upper limit for eukaryotes is 60 degrees Celsius, with most being incapable of growing, or more appropriately reproducing, in temperatures of excess of 40 degrees Celsius, with the highest internal body temperature, that of the somber hummingbird, being 45 degrees Celsius, and this likely represents an upper limit for multicellular life. Now, there is an animal known as the Pompeii worm, which lives in water hotter than 50 degrees Celsius, but its larvae can't live in temperatures above 20 degrees Celsius. So, while there are animals who could possibly survive under these conditions, they couldn't reproduce. Furthermore, the oldest metazoan hydrothermal community we found dates to 430 million years ago, meaning that if animal life could possibly adapt to reproduce in temperatures this high, they would have done so by now. As such, pretty much all multicellular life will likely go extinct 1 billion years in the future. So, by the time this penultimate mass extinction happens, the fauna would be as different from that of today as the fauna of today is from the fauna of 150 to 360 million years in the past. Of course, we can't predict when the world will become inhospitable to animal life with 100% certainty. A recent paper by Graham et al. Predicted the global temperatures to exceed 50 degrees Celsius at 1.8 billion years from now. If this is the case, then yes, it's theoretically possible for us to get a world as far removed from the present as the present is from the early Paleozoic when invertebrates occupied the ecologically dominant niche as vertebrates do now. But this would also require the transition of the background extinction rate from an exponential decay pattern to a sine wave one within the next few tens of millions of years. Looking at the plot, this doesn't exactly seem likely. It's also worth discussing what differences in faunal composition could mean in this context. From the Permian to the present, we do see a kind of back and forth between the diapsids, i.e. reptiles, and synapsids, that being mammals and their distant relatives. In the Permian, the synapsids, or the incorrectly described mammal-like reptiles, dominated, while in the Mesozoic, the diapsids, which include the dinosaurs, dominated. But then the Cenozoic comes around, and the synapsids in the form of the mammals dominated once more. However, this interpretation of prehistoric events seemingly posits that mammals and reptiles are two fundamentally different kinds of animals. But there are no separate kinds of animals. There are clades within clades of organisms, i.e. a twin-nested hierarchy, and both mammals and reptiles are part of the larger amniote clade. The common ancestor of all living amniotes lived 315 million years ago, or 250 million years before the KPG extinction. Placentals and marsupials split from each other around 175 million years ago, meaning that 75 million years in the future, they will be as distantly related to each other as dinosaurs were to mammals at the end of the Cretaceous. The common ancestor of all living placental mammals lived roughly 90 million years ago. So, in 160 million years, the descendants of weasels and hyraxes will be as distantly related to each other as our distant ancestor, Purgatorius, was from the T-Rex it was hiding from. Oftentimes in Spec Evo, to make a truly unique setting, world builders will have one of the major groups of animals, such as reptiles, replace mammals as the dominant terrestrial clade, in a kind of reversal of the end Cretaceous extinction. However, if a mass extinction happened 100 million years in the future, which caused marsupials to replace placentals as the preeminent group, it would be, at the time, as profound a change as the mammals replacing the dinosaurs after the KPG extinction. So, when judging how earth-shaking a faunal shift will be as the result of a future mass extinction, instead of looking at how distantly related the former and subsequent occupiers of a set of niches are today, one should consider how far apart they will be at the time of said extinction. We can take this further and say that since the common ancestor of all animals lived 665 million years ago, the shift to a vertebrate world some 250 million years later was profound as the mammals replacing dinosaurs some 65 million years ago, even though we currently see mammals and reptiles as closer to each other than either are to squid and crabs. So, instead of thinking about how to replace the preeminent animal groups today with something else, Spec Evo authors should also consider how diverse said groups could be in the distant future. For example, instead of continuing the synapsid-diapsid/sauropsid back and forth we've seen since the Permian, you could have a similar dynamic between the major groups of placental mammals, that being Aphrotheria, Xenarthrans, and Boreoeutherians. Thus far, we've discussed what the ramifications of the declining background extinction rate will be for the future of evolution of life, but now I think it's important to address why that is. Well, Darwinian evolution is best described as the non-random survival of randomly varying replicators. Basically, random mutations will occur, some of which will make an animal more fit to occupy a given niche, and when that happens, it will be better adapted than the species who previously filled the niche. Once the new species occupies the niche, there's always the possibility that a second newcomer will undergo a mutation that would make it even better at filling its role. But, since the second animal is more suited to fill the niche than the first, the third species would require a mutation that would give it an even bigger jump in fitness to fill the niche than the second, thus the odds of this happening are smaller. As a result, faunal replacement rates, and by implication the background extinction rate, will decrease over time. Once metazoan niches came into being 500 million years ago, it was more of a toss-up with regards to who filled which roles. However, as time passed, natural selection selected clades that were better and better suited to fill given roles in the environment. To paraphrase and build on what was said by a Natural History channel, animals didn't come to occupy the niches they do by stumbling into them. They have a suite of anatomical, physiological, and behavioral features which make them good at what they do. Going back to niche succession, the aforementioned jump made by a niche successor wouldn't have to be as big if the usurping organism occupied a similar niche. It's for this reason that we tend to see closely related organisms fill similar niches in the environment, i.e. insects occupying myofaunal niches, birds occupying flying ones, and ray-finned fish occupying nectonic ones. As the member of those clades become better and better adapted to fill these roles, the harder it will be to boot them out, and we can see examples of this. When Spec Evo authors try to make a Mesozoic 2.0, one strategy is to have living dinosaurs, i.e. birds, replace mammals as the dominant terrestrial fauna. But oftentimes when birds evolve flightlessness on small islands and mammals are brought to them, they usually overpredate or outcompete the flightless birds. Conversely, it's believed that predation pressure by hawks and falcons largely prevents flying mammals, that being bats, from occupying diurnal niches, keeping them nocturnal in a manner similar to how predation pressure by carnivorous mammals often restricts flightless birds to islands. This is why a future where different groups of mammals are vying for the ecologically dominant roles is more probable than a reversal of the KPG extinction, with diapsids becoming dominant once more. There are, of course, exceptions, but these exceptions don't mean that planetary spanning role reversals are realistic. Birds simply have physiological and anatomical features which make them more suited to fill airborne niches, while mammals have features which make them more suited for terrestrial roles. Of course, all of this discussion is about probability, and while we can say it's unlikely, given what we've seen in the past, that a planetary niche toss-up can occur, there are some scenarios by which this could happen. Apart from the background extinction rate, there are sudden pulses or mass extinctions. These are caused by a variety of factors. The KPG extinction was famously caused by an asteroid, and the end-Permian extinction was caused by the Siberian traps erupting. These are usually so destructive that for a time they render many niches inviable, causing the organisms who occupy them to go extinct. This then opens up opportunities for the niches to be reoccupied by other organisms. A future mass extinction could devastate the vertebrates, opening the niches they occupy for invertebrate animals. But would the extinction have to eliminate vertebrates, or would simply disproportionately affecting them be sufficient to open up the niches for invertebrates? I would argue it would probably have to eliminate them. Oftentimes, there will be a clade of organisms who recently underwent an adaptation which made them better equipped to fill a certain niche, but they are competitively excluded by the organisms who already fill it. But once a mass extinction happens, the niche is opened up, and the other clade can get its foot in the door, and from there outcompete the remaining members of the first clade occupying similar niches. This is known as an alternative stable state. One example of this can be seen in the extension of the carnivorans, a clade which includes the preeminent terrestrial mammalian predators such as cats, dogs, bears, hyenas, weasels, raccoons, and mongooses. The first members of this group appeared around 50 million years ago, but they were competitively excluded from the role of apex predator by other groups of mammals, most notably creodonts and mesonychids. Then, 35 million years ago, the end Eocene extinction exacted a heavy toll on the mesonychids and creodonts, allowing carnivorans to occupy the apex predator niche in certain parts of the world. From there, the carnivorans spread across the continents, outcompeting the creodonts and mesonychids, driving them to extinction. Vertebrates have shown themselves to be more capable of filling most ecologically dominant niches than invertebrates. This is for a variety of reasons, such as their internal skeletons allowing for larger sizes, and more efficient respiratory and circulatory systems, facilitating a more active lifestyle. So, even if a mass extinction happened and wiped out most vertebrates, their niche could temporarily be occupied by an invertebrate, but odds are they'd be outcompeted by other vertebrates. This then raises an interesting question. What could wipe out the vertebrates? It's hard to say, but in The Future is Wild, they had increased volcanism, a pretty generic cause of mass extinctions, wipe out the tetrapods to give rise to a new world. But tetrapods have shown themselves to be capable of surviving mass extinctions caused by volcanism. So, if you do insist on wiping out the vertebrates in a hypothetical future, and you want your scenario to hold water, you'd better give a good explanation as to why the extinction impacted vertebrates so much. Just like ecological succession, mass extinctions aren't stochastic processes. Those who survive do so because they had a suite of adaptations that allowed them to push through. But while a future dominated by invertebrates may seem unlikely, what about an alternative prehistory where other phyla of animals got the edge in the early Paleozoic? Well, it's more likely than in a future scenario, but vertebrates seem to have the features which allow them to become so successful, such as the internal skeleton, closed circulatory system, and active respiratory system since the Cambrian explosion. As such, they could have been seen as predisposed to ultimately fill the ecologically dominant roles. Going into the field of astrobiology, it's likely that the animal-like aliens who come to fill the megafaunal niches would have similar features to vertebrates, making the idea of a world dominated by insectoid-like aliens pretty unlikely. Some might say I'm biasing this view too much based on what we see on Earth as opposed to what could possibly exist on other worlds. However, on Earth or any other planet, the square cube law is going to be a bigger hindrance on an exoskeleton than an endoskeleton. All too often, in their attempts to make worlds that seem unfamiliar to us, Spec Evo authors make the current cast of large animals seem very fragile and give the impression that they'll keel over in the face of the slightest perturbation to the environment. But in reality, they've been fine-tuned and hardened by over 500 million years of evolutionary trial and error. On top of that, the rapid climactic fluxes we've seen over the course of the past 2 million years had also weeded out many of those susceptible to environmental perturbations. One reason a lot of the ecologically dominant animals may seem vulnerable is due to the fact that they have large sizes. After all, being larger means you have a lower reproductive rate, and thus it will take longer to adapt to a change in the environment, and often a given species won't have enough time to adapt. Well, not quite. While low reproductive rates, and thus large sizes, makes it harder for animals to adapt and thus more vulnerable to extinction, This is one of many factors that contributes to this. There are also specialist animals, those adapted to thrive in one environment, and generalists, those adapted to get by in many. A specialist can have high reproductive rates, but these will mean nothing if they can't survive, or at the very least reproduce, in a new habitat, which came about as the result of an environmental perturbation. Meanwhile, many large animals are generalists, with some, like wolves, able to survive in a wide variety of habitats from scorching deserts to freezing tundras. Furthermore, being large does give an advantage in dispersal. While bigger animals will need more food over the course of their lives, they can often go weeks without food while trekking for hundreds of kilometers, allowing them to find new pastures should their home range no longer be able to sustain them. Meanwhile, many smaller animals can't go a day or move more than 1 kilometer without food. So, being big isn't as big of a hindrance as a lot of Spec Evo authors often portray. Oftentimes, they want to replace the cast of large animals with smaller ones, and even though being larger does, on average, make larger animals more vulnerable to extinction, so long as there are other megafauna alive, any smaller species trying to fill the niche of the recently extinct species will face competition from other megafauna who, even though they won't be able to adapt as quickly, will more often than not have a head start in filling the vacant role. In order to get a world where the megafaunal niches are occupied by the descendants of the smaller animals today, you'd pretty much have to wipe the megafaunal slate clean, and if prehistory is anything to go by, you need a mass extinction on par with the Big Five to accomplish this. Yet, Spec Evo authors will often use some vague explanation like climate change. Although, to be fair, smaller animals will still occasionally evolve to occupy megafaunal niches. So, if you give it enough time, eventually, the trickling in of the descendants of smaller animals into these niches will eventually replace the descendants of virtually all existing megafauna. However, this would probably take tens or even 100 million years. In Spec Evo scenarios with existing megafauna replaced by current small animals, the descendants of the small animals often look like enlarged versions of their modern-day ancestors. But, if enough time had passed for a megafaunal replacement, the descendants of these smaller modern animals would have largely changed beyond recognition by the time most of them got the chance to fill the megafaunal niches. Part of the reason a lot of the dominant animals may seem vulnerable is because many are currently suffering. However, we are currently in the midst of the 6th mass extinction, and during mass extinctions, pretty much everyone struggles. But, this anthropogenic mass extinction could in principle be what wipes out all modern megafauna. So, what kind of animals would be the most likely ones to inherit a post-human world? Well, what's obvious to anyone who studied conservation biology is that some groups of animals have done better in the face of human civilization than others, so it would make sense that these would inherit the world. But again, it's not that simple. While some animals have been able to persist in the face of human development because they're hardy generalists who can persist through just about anything, others have become more abundant because of the unnatural abundance of food which came about as the result of agriculture. Most prominent of these are rats and mice. Furthermore, anthropogenic warmth has allowed some species to expand their ranges closer to the poles than they could otherwise, such as the Virginia opossum. So, while it's tempting to think that such species would rule the world once the 6th mass extinction has passed, in reality, many will crash once humans are no longer present to provide them with the resources which allowed them to live in such high abundances. Some Spec Evo world builders take this further and assume that the animals who are doing well now will fare better in any future mass extinction. But each mass extinction comes with its own trials and tribulations. Many of the species who are thriving as the result of human civilization are adapted to reproduce rapidly when resources are abundant. Conversely, there are those which have lower reproductive rates, but can withstand times of resource inavailability. An evolutionary trade-off, being able to thrive in abundance versus being able to survive in times of scarcity. Oftentimes, mass extinctions are associated with scarcity, so a lot of the animals who have been able to capitalize on human civilization would do worse in such a situation. In summary, there's a tendency to see the prehistory of the Phanerozoic as fundamentally different kinds of animals vying for the ecologically dominant niches. Looking forward into the future, it's tempting to see this back and forth continuing, with reptiles replacing mammals in the distant future, and invertebrates taking those niches in the even more distant future, as was the case in The Future is Wild. Basically, we assume that just as the major groups of animals have modern descendants more distantly related to us as we go further into the past, the further we go into the future, the dominant animals will have modern ancestors increasingly distantly related to us. But this interpretation is based on an overly static view of classification. All animals are part of a parent clade, that being metazoa, with many smaller clades within it, and smaller clades within them, and the further you go back in time, the more closely related the major groups will be. Instead of a continuous back and forth between separate lineages of animals, we have different groups diversifying to fill given sets of niches because they have a suite of assets which make them well suited to fill those roles. I mean, there will initially be some back and forth, but they'll settle into their roles as trial and error selects animals better adapted to fill these niches. As different clades of animals get better and better at what they do, the greater the perturbation that will be required to drive them out, hence the declining background extinction rate. So, in the future, instead of continuing past arms races between clades which have existed for a long time, similar arms races will be playing out between the descendants of groups of animals who are closely related now. Remember that when synapsids and sauropsids were vying for control in the early Triassic, they were as closely related to each other as the major groups of placentals are now, and when nautiloids, jawless fish, and sea scorpions were vying for control in the Silurian and Ordovician, they were as closely related to each other as marsupials and placentals are now. Also, a pet peeve of mine is that we see huge faunal changes in Spec Evo scenarios, but the plant life is largely the same. If you want to make the fauna as different from the fauna of today as the fauna of today is from the Mesozoic or Paleozoic, the flora should see a similar degree of alterations. Cycads were preeminent in much of the Mesozoic, and lycopsids were common in the Paleozoic, so if you're going to try to bring previously dominant groups of animals back to the forefront, there should also be some unrecognizable flora too.